we have been looking at the modified equation. Just remind you, the modified equation is the actual equation that we think we are solving when we get our approximate solution to the original equation. In employing the modified equation, we have defined consistency, right, and well, auxiliary on the side I defined what is convergence. We also saw that the modified equation to our original wave equation, the original wave equation the way we were looking at it had a 0 right hand side, right, but the modified equation ended up having terms that were of the form, instead of being 0 had some coefficient second derivative of x, and we had things with third derivative of x and so on. We wrote it up to and including the fourth derivative, right. So we then asked the question, just take one such term, the equations are linear, why don't I deliberately add, right, a term on the left hand side, on the right hand side, which has dou squared u dou x squared. Mu2 is a constant, okay, and very suggestively I have called it mu2. Clearly I am going to have a mu3 and a mu4, fine, okay. Now for this equation I am just repeating what we did at the end of the class. We said that a solution could be written in terms of Fourier series, right, and I will write one term, it is still a solution, so that u could be written as an exponent I n, I think I decided to get rid of the 2 pi and l, right, x minus a t. This was for the original equation. We decided to go the semi inverse route, which means that we are going to try out, come up with a candidate solution. We will guess that the solution to this equation is in this form, and that gives us one disposable constant b that we need to determine, fine, all the others are fixed. Now since I know I am going to add extra derivatives, let me just write out all the derivatives that I require, okay. So dou u dou t, right, and then we can just substitute, we can keep track of this and substitute whatever we want. Dou u dou t is what do we get? So if you differentiate this, right, if you differentiate this, or we will use product rule, so you will get the sum of two terms, whichever way you want to do it. So you will get a u times INA, that comes from differentiating the first one with a minus sign because it is a minus AT, plus B. Is that fine? What is dou u dou x? U times, this is u times, I will put a star, u multiplied by u times, it is not u of, maybe I will use a square bracket, u of u times IN, that is it, that is it. What is dou squared u dou x squared? So you will get another IN, every differentiation with respect to x you will get an IN, so that will become a minus n squared u dou cubed u dou x cubed gives me an IN times that minus IN cubed u, and finally dou to the fourth u dou x to the fourth is n to the fourth times u. Is that fine? Everybody is with me? Now you can just work it out. So we will work it out first for this equation. It has only a second derivative term. So clearly all of them have u as a coefficient, that will go away. So if I substitute, the first term is going to give me a minus INA plus B, and the dou u dou x has an a multiplying it, so that will give me a plus AIN, which is the whole point, which is why our original equation was satisfied, equals mu2 times minus n squared, minus mu2 times n squared. Fine, that is B. So this tells me that for this equation, for the equation that we have for this equation, this tells me that the B here should be minus mu2 times n. Okay, fine. So what does that mean? What does that, what's the implication of that? U, I will just write it out as AN exponent, I will just write it out again, IN x minus AT e power minus mu2 n squared t. So what does this tell us about U? The added terms. If this weren't there, it is just a bunch of sines and cosines, right? The amplitude depending on the n, sin x, sin 2x, sin 3x depending on the n, and the amplitude is an, and the an does not change, okay, it does not change with time, the n does not change with time, it only changes with wave number but it does not change with time. Whereas what has happened now is because it is being multiplied by this mu2 n squared t, the solution is going to decay, okay. I prefer the word decay. In literature very often we call it a dissipative term. So it is called a dissipative term or dissipation. The scheme is said to be dissipative. So the solution decays, is that fine? The addition of the second derivative term, the solution decays, given that, when does it decay? Mu2 has to be positive, mu2 has to be greater than 0. So you get this decay if mu2 is greater than 0, is that fine? So far it looks okay, but there is something else that is interesting, it does not just decay, there is an n squared term here, okay. So it basically says that higher frequencies decay faster than lower frequencies, okay. So higher frequencies will decay faster than lower frequencies. If mu2 is negative, the exponent here is positive, the solution will diverge, fine, is that okay? So what we are saying is, see, remember I have added this term to the right hand side because such a term appeared in my modified equation. And what is the modified equation? The modified equation is the equation to which my approximate solution, the solution that my program is generating, is a solution to the modified equation. So the modified equation has this extra term, has the second derivative term, the modified equation has the second derivative term, and the mu2 is negative, my scheme is going to diverge, is that fine? And mu2 is positive, my scheme will converge, right, my scheme will be stable, fine, my scheme will be stable. We have the added information about what our algorithm or the solver does. I want you to understand, by writing out this equation we are saying something about how our program is actually going to behave. You understand that we can look at the modified equation and make an observation, that is what we are trying to do. This basically says that a program that you write using a scheme which has the second derivative term will cause the high frequencies to decay faster than low frequencies, given that mu2 is positive, right, and if mu2 is negative, high frequencies will diverge faster than low frequencies, fine, okay, right. So this is the property that we are able to get. So what happens if we have a third derivative now? Let us consider the situation where you have dou u dou t plus a dou u dou x equals, and we add a mu3 dou cubed u dou x cubed, okay, and in this case b happens to be, from the third derivative b is minus I n cubed mu 3. Is that fine, everyone? So the u for this equation is a n exponent I n x minus, well, the b also is going to have an in it, either we can take it in one step or maybe we will do it in two steps. Let me not hurry through it. At exponent e power minus I n cubed mu 3 t, okay, and we can in fact combine these terms. So this gives me a n exponent I n x minus a plus mu 3 n squared t. Is that okay? Okay. So what was the coefficient that was multiplying the t? The coefficient that was multiplying is the physical speed with which, right, it was the speed with which our equation was propagating the signal. You understand? Whatever you are modeling, whether it was u or whatever it is that you are modeling, this was the speed with which it was being propagated. That speed has now changed. Okay, that speed has, so the addition of the third derivative term, we have a purely complex term here, it is not going to decay, there is no real component, it is not going to decay, it is going to keep on oscillating, it is going to keep on oscillating. Added to it, it turns out that our mu 3 term actually adds to the speed of propagation. There is worse. What does it add, right? What does it add? So of course I will say, I am saying added because I am in my mind saying mu 3 is greater than 0, it adds. If mu 3 is greater than 0, it adds. If mu 3 is less than 0, it subtracts, right? So it adds to the speed, propagation speed, and mu 3 less than 0, it will subtract, okay, subtracts. But there is worse, the speed that it adds depends on the frequency, right. So in this case if mu 3 is greater than 0, high frequencies will travel faster than low frequencies. Am I making sense? High frequencies will travel faster than low frequencies, that is basically what it says. Not only is the function that we are monitoring, not only is it propagating at the wrong speed, right, but if you decompose it using Fourier series into its component frequencies, right, the high frequency will travel faster than low frequency. Am I making sense? This is called dispersion. Dispersion, right. In a technical context, most probably the first time you encountered dispersion was possibly when you were looking at Newton's experiment with optics, right. That is most probably the first time where you saw dispersion of light and light pass through a prism at an angle, right. Dispersion, the fact that different wave numbers are traveling at different speeds causes, enables you to see that white light is actually has a spectrum associated with it, okay. So that is dispersion, that is most probably the first time you most probably encountered it is when you are sharing a bag of potato chips or something of that sort, where you know that if you take a standard bag of potato chips, right, the larger wave numbers, the more interesting wave numbers, no, I should say the smaller wave numbers, larger wavelengths, the more interesting wavelengths tend to be on the top and the fine dust tends to be in the bottom. So the person who grabs the bag first gets the biggest pieces, right, and invariably, so any container, if you look at it, you will see that the dust tends to settle, the, you know, if you have aggregate material, you will see that it gets, there is a process of dispersion as you disturb it, where the higher frequencies end up at the bottom and the lower frequencies end up at the top. The larger pieces end up at the top and the finer dust ends up at the bottom, and you get a distribution. So it is always what you have known intuitively, that you should grab the potato chip bag right in the front, is a fact, because purely because of dispersion, right. That high frequencies, in this case there is a separation that takes place, right. You would like the signal to be in a certain form, but there is a separation that takes place. What does that mean? Well, if you had, what that basically means is that if you have an initial condition which is like a step, and you do a Fourier series expansion for this, we will ignore ideas of Gibbs phenomenon and all of that, right. You do a Fourier series expansion for it, that as it propagates in time, right, that we expect not to get a step but to get something that is wavy, simply because the way you do Fourier series, all of the coefficients, all the wave numbers, they combine together in such a fashion as to wherever there is a peak which you do not want, it is cancelled by a higher frequency, you understand. And if they are travelling at different speeds, what gave you a sharp step in the beginning, as it propagates, because the different frequencies are travelling at different rates, they will not quite add up exactly, okay. Am I making sense? They will not quite add up. So there is a, in a sense, if you look at the one that is propagating at the right speed, there is a phase error that is introduced into the system. Some of them are not in the right phase, they are not all adding up together, right, properly. There is a phase error that you are accumulating. That is basically what happens. So that is dispersion. What about fourth derivative? Do u do t, a do u do x, mu fourth do x to the fourth. We do not have to go through the whole process, right. B equals mu 4 n power 4. So this is just like the second derivative, there is a difference though. So u is a n exponent I n x minus a t e power minus plus mu 4 n power 4 times t. So for stability we require, you will have stability if mu 4 is less than 0. Mu 4 has to be less than 0 for stability, for decay. If it is not less than 0, it is going to diverge, I want to emphasize what we are doing here, though we seem to be looking at these equations individually with these terms thrown in. Looking at this behavior, you can look at your modified equation and then determine what is the behavior of your program. That is the idea, okay, that is the idea. This has an n power 4, this is a lot worse, this has an n power 4. Am I making sense? I mean, you can just look at, if you consider wave number 2 versus wave number 1, 2 power 4 is 16, right. If you look at wave number 1 versus wave number 10, now you are talking about exponential raised to the power 10,000. So this is really, high frequencies are just completely being eliminated extremely rapidly. But again we have the same story, that high frequencies decay faster than low frequencies, but because we have an n power 4 involved here, right, and the decay occurs when, I keep doing this exponent, when mu 4 is less than 0, right. If mu 4 is greater than 0, it is going to cause a divergence, fine, and high frequencies will then diverge faster than low frequencies, right. So this seems to tell us that maybe we have to be a little worried about the high frequency content. Is that fine? Is that okay? Right. What about the modified equation? Do you remember the modified equation? You remember the, well, you may not remember it. just to recollect, remember that I said that in order to, in the modified equation you have time derivative terms, right, and to eliminate the time derivative terms you should really use the modified equation itself to eliminate the time derivative terms, okay, and all the mixed derivatives that come because of that, fine, right. What I did in class last time, I just basically used the governing equation. There is a reason why I did that, right, because we need that equation also, though it is not really the true modified equation, we need that equation also. What I will do now is I am not going to do FTBS. Originally I thought maybe I would do FTBS, I am not going to do FTBS, I will save a little time. I got myself a cheat sheet from my book, which I have got a little table, right, of all the terms, second derivative. So we have seen second derivative, third derivative, fourth derivative. What do you expect to be the nature of the fifth derivative term if there is one? You expect it to be dispersive, right. So for the linear wave equation, right, if you add to the right hand side, if there somehow you add to the right hand side even derivative terms, the sign may change, but it is likely to be decay if you pick the right coefficient, right, and if you add odd derivative terms, it is not going to decay, but it is likely to be dispersive. Whether high frequencies travel faster or travel slower will depend on the coefficient that term has, okay, that has to be determined, right. So just looking at second, third, fourth, we can sort of guess, because we can see that you get I squared, I cubed, I to the fourth and so on. So it is very clear that it is going to become real, imaginary, real, imaginary, and the sign will keep flipping, okay. So that is very clear, that process is obvious, okay, as to what is going to happen. Let me just write out this, table for you. So what I am going to do is I am going to write forward time central space, forward time forward space, forward time backward space, and this will look different from what I did last time, because in this case I am actually using the modified equation to eliminate the time derivative terms. Is that clear? Okay. So this is the coefficients that I get for FTCS will look different, fine. I will show you when I do a demo, I will show you an easy way by which you can calculate this, otherwise it is a pain. I mean you have to do it. I have done all of these manually, because even though I have done them using a symbolic manipulator, I did not trust the symbolic manipulator, I actually did it manually, right. So but what I will do now is I will have here, let me first write mu2. So this is the mu2 term for FTCS. So you get a minus A delta x by 2 times sigma, fine. What is sigma? A delta t by delta x. So where possible I will write it in terms of sigma, because sigma is something that seems to be significant for us, it showed up in all our stability conditions and so on. So I am going to write it in terms of sigma where it is possible. So then FTFS mu2 happens to be minus A delta x by 2, so that is the same for all of them, 1 plus sigma, and FTBS is A delta x by 2 1 minus sigma. You understand? So right here you can see this is negative, right, unless something happens to say this is negative, that could be positive, right, that could be positive, which is what we got, 0 less than sigma less than 1, we got a stability condition. It is possible you may not always get the stability condition out of the modified equation, or you may not always get the perfect stability condition out of the modified equation, but in this case it actually worked, okay. So it really shows that whether if mu2 is negative you get unstable situation, if mu2 is positive you get decay, right, and the solution or the algorithm is stable. Is that fine? Okay, right. So what we did with the stability condition we actually got here. What about mu3? Mu3 is a bit of a mess, So that is going to be minus a delta x squared by 3 factorial 1 plus sigma 1 plus 2 sigma squared. Fine, and a minus a delta x squared by 3 factorial. I could have most probably saved a little space by keeping all the constant, these a delta x squared, those tend to be the same, 1 plus sigma into 1 plus 2 sigma plus 1 or 1 plus 2 sigma. And the last one is minus a delta x cubed, I am sorry, delta x squared by 3 factorial 1 minus sigma into 2 sigma minus 1. I am writing it a little big, if you do not mind. I will write the third column here. So that is mu 4. So you get a minus a sigma delta x cubed by 12 2 plus 3 sigma squared. Okay. So do not say, first thing, just do not take this down and you are happy with it, you should try to check at least a few of them. There are enough of you that you can take bits and pieces and check it out. The other thing is, you should at least do the using the wave equation instead of the modified equation to eliminate the time derivatives, to see what is the difference between what I have given you and what you would get there. Okay, and you will get a little practice actually doing the modified equation, which is a good idea for you to do. Okay, so then you have a minus a delta x cubed by 4 factorial 1 plus sigma 6 sigma squared plus 6 sigma plus 1, and FTBS, right, our star performer amongst the 3 of these, right, is a delta x cubed by 4 factorial 1 minus sigma 6 sigma squared minus 6 sigma plus 1. Okay, that is the full table. Is that fine, everyone? So you look at this. This basically says that for all of them you have dispersion. For all of them you have dispersion. Fine, and depending on what happens, so depending on what values that you take, the sign can actually change. It is possible for the sign to change, right? In some cases not, in some cases, right, and in this case what happens, you have to see whether it is high frequencies travel faster. So I will allow you to work through this to see what happens. Okay, so you have FTFS, FTBS, all of them can be dispersive, and you have mu 4, these two have negative quantities. So you say, wait a minute, if it is negative they should be stable, right, but apparently it is not enough to stabilize, apparently it is not enough to stabilize. Okay, and that is likely because of the n power 4, which is more stabilized than the wave numbers close to 1. Okay, and what do we have here finally? Here we have positive, it is supposed to be destabilizing, but apparently it is not dominant enough to actually create problem for us. Okay, right. So we have got the second derivative, third derivative, fourth derivative. Looking at this, I would suspect that maybe the higher derivatives are not really that important. Okay, as a first order conclusion that I come to, right. If you were to try it out, see, we have not actually run programs yet, right, but if FTBS actually does deliver, right, we can conclude that the higher derivatives maybe aren't that important right now. We may find use for them later, right now it looks like they are not that important. Any other observations that we can make? If you set sigma equals 1 for FTBS, it looks like all the terms in the modified equation have a 1 minus sigma. If you set sigma equals 1, and it turns out, by the way, it is a fact, if you write out the terms, the general terms in the modified equation, all of the terms will have a 1 minus sigma. So in the case of FTBS, if you set sigma equals 1, your approximate solution is a solution to the exact equation, the original governing equation. Okay, that is nice, but remember, what does that mean? See, you can't just say, oh, I am solving the original equation. We are solving the original equation, but our function is still represented only using 11 grid points or 100 grid points or 1000 grid points. We still have a computer representation of the function. That function is being propagated at the right speed. Our approximate function is being propagated at the correct speed. Our approximate function is being propagated the way it is supposed to be propagated by FTBS, by the wave equation. That is all it means. If sigma equals 1, the modified equation for FTBS becomes identical to the original equation. Okay, so our approximate solution actually satisfies that equation. It is just that it is an approximate solution still. Am I making sense? Okay, because it is a representation using a finite number of points. If you were to try to represent that step function that I talked about earlier using a finite set of points, what you would actually get would be a ramp. What you would actually get would be a ramp. There will be a value here and the next value will drop, and somewhere in between there is a step. What you will actually get, this is about the best that you can do if you are going to be using linear interpolants, if you are going to use hat functions. This is the best that you can do. So the actual representation will be a ramp. All that says is, if your initial condition was a ramp, everything is fine. If your initial condition is a step, then there is an approximation in the representation of that step. Is that okay, everyone? Right. So what we have seen is that we have this, we have the modified equation. I have written it in a strange fashion, but we have the modified equation for all three of these. You can try out the modified equation. What have we left out? BTCS, right? And as I said, you can use the wave equation itself, and a little exercise, just try it out, make sure that you are able to do it, get the modified equation for the rest. Fine. Are there any questions? Questions? Everything is fine? Okay. So then what do we have now? I will go to this board here. What do we have now? So the question is, we have seen that because of mu4, we have seen that because of FTCS having this term in the front, up front, right, because FTCS has this term up front, that the coefficient being negative, that is the reason why it is not working, right, that is the conclusion we draw from this analysis. And in this case, for sigma between 0 and 1, this coefficient being positive, that is the reason why this thing is working. Okay. So there seems to be a case for upwinding, that is one thing. There is another thing, we can ask the question, well, what actually is the difference between the two? After all you are doing is, in the forward time central space part, you have a up plus 1 at time level q minus a up minus 1 at time level q divided by 2 delta x, right. I have left out the time level q, fine, right. And in the case of FTBS, what you have is a up time level q minus a up minus 1 time level q divided by delta x. Really, between the two schemes, that is the only difference. Between the two schemes, that is the only difference, and the modified equation changes in the sense that a second derivative term, the sign of a second derivative term changes. So what happens if you subtract one from the other? What is the difference between the two? Let me ask the question that way. What is the difference between the two? Right. So the LCM is 2 delta x, that is easy. UP plus 1 minus UP minus 1 minus 2 up plus 2 up minus 1. And this gives me up plus 1 minus 2 up plus up minus 1 divided by 2 delta x. I can multiply and divide by delta x, right. If I multiply and divide by delta x, this gives me a delta x, I take the 2 back here, delta x squared. That looks familiar, that is a second derivative, right. So this sort of brings a little closure here. So the difference between the modified equations and the difference between what we are doing here, between central differences and forward, so if you are doing and backward differences, if you are doing upwinding, what you are effectively doing is you have taken central differences and added some kind of dissipation, okay. You have taken central differences and you have added some kind of dissipation. This is the exact amount of dissipation that you have added, which caused a change to your modified equation. Is that fine, right. So there is a school of thought that basically says, why not add the dissipation ourselves? There are two ways that you can pose it. So basically what we are saying is FTBS equals FTCS plus dissipation. Okay. So it is almost as though there is a possibility that any scheme can be written as FTCS plus add on terms, okay. That is one possibility, but right now we do not go that far. We basically say, oh, I can take FTCS and I can add any amount of dissipation that I want to it. I can take FTBS and add any amount of dissipation that I want to it. Is that fine? That is what it seems to say. I can take FTCS and add any amount of dissipation I want to it. So you can just basically say UPQ plus 1 is UPQ plus minus sigma by 2 UP plus 1, oh, I have gone to superscripts, suddenly gone to superscripts. And then you can decide to add yourself, you can decide to add some kind of a term that looks like a mu2 times a second derivative, okay, right, because after all, I mean, anyway, see, you are not solving the original equation, you are only solving the modified equation. So why not pick the modified equation that you are going to be solving? That would be the argument, why not pick the modified equation that you are going to be solving? Okay, so if you know the modified equation, you can knock out whatever terms that you want in the modified equation, that is one way to look at it. Or you know the modified equation, it has some structure that you do not like, you can specifically modify that structure to something that you like, fine, okay. Now you can ask the question, is it possible for me to take FTCS and just eliminate the dissipation? Is it possible for me to take FTCS and eliminate a term? Is it possible for me to take, I should restate that properly, is it possible for me to take the modified equation of FTCS and do something to FTCS so that one term disappears, the second derivative term disappears, the third derivative term disappears, okay. In order to do that, if you want to do it sequentially, that is, you want to eliminate the second derivative term, in order you want to eliminate the third derivative term, that term that you use, the term that you add here in order to eliminate a specific component of the modified equation, just so that you understand what I am saying, dou u dou t, so it is not in the air, I am not saying this term, that term and so on, equals, and there is a dou squared u dou x squared, dou cubed u dou x cubed, dou to the fourth u dou x to the fourth, and so on. Let us say we just decide that we want to get rid of this term, right, you want to get rid of this term, or you want to get rid of these three terms, okay, but you are going to do it starting at the second derivative, you are going to eliminate terms from the modified equation. Do you understand what I mean? That means I have to add something to FTCS so that these terms disappear. Okay, this is something that I want you to think about now. To determine what is the term that needs to be added, you have to use the modified equation derived from the original equation. You have to use the modified equation derived from using the original equation in eliminating the time derivatives, and not the modified equation derived from the using the modified equation. Do you understand what I mean when I say modified equation derived using the modified equation? The modified equation has time derivatives and spatial derivatives. We eliminate the time derivatives using the modified equation. We eliminate the time derivatives using the original equation. If you want to eliminate any term in this, you should use the equation. I am not going to give you an answer here, you think about it. You have to use the modified equation that comes from this and not the modified equation that comes from that. Okay, you may need, you ponder on it and you will see why it is that I told you to derive the modified equation using this term. So you can actually systematically add terms here. To answer the question, what term shall I add here in order to eliminate this? You should derive the modified equation using the original equation, right, to eliminate the time derivative terms. Is that clear? Okay, you have to go back in order, that statement may be a little confusing, you will have to go back, look at how we derived the modified equation and you will understand what I mean. Fine. Okay, so it is possible for us to eliminate it, it is possible for us to actually add it. If you were to deliberately add a second derivative term, right, if you were to deliberately add a second derivative term, it is referred to as artificial viscosity. The Navier-Stokes equations has a second derivative term which is viscosity. This looks like that, so this is called artificial viscosity. The term that shows up in your modified equation naturally because you just did a discretization is called numerical viscosity. Okay, so this comes from your discretization, you have discretized it, so you end up with a term, a second derivative term which is not there in the original equation, right. So it looks like your equation has become viscous when it is actually not viscous, so that is numerical viscosity. Okay, the term that you add deliberately because you want to fiddle with the modified equation, that is called artificial viscosity. Fine, okay, right. Then we say, we have said now, see I just casually made a statement, you can add any amount of artificial viscosity that you want, right. Is that true? What is the consequence of that? What is the consequence of adding any amount of artificial viscosity that you want? What is the consequence of adding any amount? So if you add a large amount of artificial viscosity, what happens? Say your propagation speed is 1. Say your propagation speed is 1, right. Say your propagation speed is 1 meter per second, if you want units 1 meter per second. And since I have said that your artificial viscosity can be anything, I add mu to 10 power 6. Is there a concern? Should we be concerned? See, now you have really totally changed the equation, right. You are no longer solving, you are really no longer solving the linear wave equation, you are solving something that looks closer to a heat equation. A is so small, this is almost like dou u dou t equals mu 2 dou squared u dou x squared. Of course, we do not normally say mu 2, there we use the term kappa, right, for thermal conductivity, thermal diffusivity actually, but anyway, right, I will use the term conductivity, thermal diffusivity, right. So it would essentially degenerate to this equation. What is the stability condition associated with this equation? If you were to apply FTCS to this, applied to heat equation, FTCS applied to heat equation, somewhat of a rapid fire quiz here. So UPQ plus 1 is UPQ plus kappa delta T by delta x squared. I am not really doing this from memory, I am sort of working it out in my head. You can work it out in your head, right? UP plus 1Q minus 2 UPQ plus UP minus 1Q. Is that fine? We have a term here that looks similar to what we had earlier, like sigma. We call this lambda. Fine. So we will substitute our exponential, we will go through that same process. So UP plus 1 Q is e power I theta UPQ, where theta was n delta x or n delta x by L n delta 2 pi n delta x, whichever however we define our interval. See, I am not even bothered now. The fact that it is a local analysis is very clear. I am not even saying how large my domain is, I am not even bothered. It just shows up as theta, and the theta will appropriately vary. Okay, the theta will appropriately vary. So this basically becomes UPQ plus 1 is UPQ minus lambda times e power I theta minus 2 plus e power minus I theta UPQ. And therefore, from our earlier stability analysis, G, did I make a mistake somewhere? Plus lambda, still stuck with wave equation, plus lambda, right. Therefore, G, which is UPQ plus 1 divided by UPQ, the gain across one time step, the amplification across one time step, is 1 plus, what do I get, e power I theta plus e power minus I theta, 2 cos theta. So that gives me a 2 lambda into cosine theta minus 1. What? And I want mod G to be less than 1. Mod G less than 1, what does that tell me? This is real, right, this is real. Mod G less than 1 tells me minus 1 less than G less than 1, fine, or minus 1 less than 1 plus 2 lambda cos theta minus 1 less than 1. Which way do we want to do this? You have to take take an inequality at a time and see what happens. You want to look at this one, okay. So if I look at that one, that tells me 2 lambda into cos theta minus 1 less than 0, or lambda should be greater than 0. What does the other condition give me? Minus 1 less than 1 plus 2 lambda cos theta minus 1. You can do this, I mean there are different ways by which we can do this, or minus 1 less than lambda cos theta minus 1 Is that right? I took this -1 over there, -2 divided through by 2. I skipped a step. Okay, fine. Then lambdas, what so what does it tell us about the cos theta -1? What can happen? What is the constraint that this gives me? Lambda is less than half. So you get lambda is less than half. We can come back to this 0 less than lambda less than 1/2 is the constraint that we get. We will come back to this. We are going to, while I will do this in a 2D context, we will come back to this. Okay, it is fine, right. So I will see you in the next class.